Alright, so for this portion, I'd like to do a few problems out of your book. So this is problem number 2.116. Right? So a communications network has a built-in safeguard system against failures. In this system, if line 1 fails, it's bypassed and line 2 is used. If line 2 fails, it's bypassed and line 3 is used. The probability of failure of any one of these lines is 0.01 or 1%. And the failures of these lines are independent events. So what is the chance that this system of 3 lines does not completely fail? Feel free to pause it and look this statement of the problem up in your book if you need to. Okay, so here's what I'm going to do. So this is number 2.116. And first thing, I'm going to write down what is it exactly that we want. We want to find the probability that the system does not fail. Okay, so it can be helpful to think about, to try to translate these sentences that comprise the events into math speak, right? Couldn't I rewrite this as the chance that maybe I could use F for fail, F complement. That's what I want. F is the event that the system fails, right? So I want to know the chance that the system does not fail. So right away, I'm thinking about the rule for complements. 1 minus the chance that the system actually fails is what that is. Okay. One of the go-to tricks when you're trying to solve a probability problem is think about the rule for complements. Oftentimes, the complementary event it's much easier to calculate the probability of a complementary event sometimes. Okay, so what is the probability that the system fails? That's the probability that line 1 fails. Actually, could I write it like this? Line K fails. Actually, I got the wrong symbol here, shouldn't it be? It's the chance that of the intersection of those 3 events, right? It's the chance that line 1 fails and line 2 fails and line 3 fails. The system's going to fail if and only if all 3 of those things fail, right? Now remember what independence allows us to do. Since those events are mutually independent, we can write this as the product of those 3 probabilities. Probability that line K fails. All right. And so, in fact, all those probabilities are the same. So it's just, and each one is 1%. So 1% times 1% times 1%. Okay. What does that turn out to be? 1 minus 0.01 raised to the third is 0.999999. So there's a pretty good chance that the system is going to be okay, right? All right, how about number 217? 2.117, excuse me, 2.117. Let's take a look at it. So an auto inspection station has 2 inspection teams. Team 1 is lenient and passes everyone of a recent vintage, all the cars that were recently made. Team 2 rejects all the cars on first inspection because their headlights are not properly adjusted or some garbage. 4 unsuspecting drivers take their autos to the station for inspection on 4 different days and randomly select one of the 2 teams. If all 4 cars are new and in excellent condition, new meaning of recent vintage, okay, and they're all in excellent condition, what is the probability that 3 of the 4 will be rejected? Okay. Now I'm going to take this to mean that basically basically Team 1 is passing everyone. Team 2 is rejecting everyone. Okay, but what happens is that the drivers are randomly selecting one of the two teams. So basically, you can think of it like this: a driver goes into the inspection station, flips a coin. If it's heads, then they pass because they get Team 1. If it's tails, then they fail because they've gotten Team 2. Okay, so basically, each driver flips a coin. If it's heads, they pass. If it's tails, they fail. Okay. Again, feel free to stop this video at any point in time. Try to work the problem out yourself. But so here's my solution to this. So this is part A. What is if all 4 cars are new in excellent condition? What is the probability that 3 of the 4 will be rejected? What is the probability that 3 of the 4 are rejected? Well, that's the probability that that maybe that the first is rejected, and then the next 3 pass, or the first one passes, the next one's rejected, and then the next 2 pass. Could I just sort of write it like this? Or the first 2 pass, and the third one is rejected, and the last one passes, or the first 3 pass and the last one's rejected, right? Can I sort of denote it like that? And maybe I should put these in braces like that. Okay. Now, by axiom 3, for our probability axiom 3, since these are disjoint events, I can write this as the probability. It's the sum of the probabilities, right? Pass, reject, pass, pass, plus, and so on, right? So this is by axiom 3. Okay, it's by axiom 3. And now, guess what? I'm going to use independence. What's the probability that the first one's rejected and the next 3 pass? It's a half times a half cubed, right? And this one is a half times a half times a half squared, right? And then the next one is a half squared times a half times a half. And then the last one is a half cubed times a half, right? I wrote it that way so that you can see that, here, the chance of passing is 1/2. And I've got 3 of those raised to the half. The chance of being rejected just happens to be a half. Okay. All right, so basically this is, the final answer is going to be 4 of those, 4 times a half raised to the 4th. So what is that? Which is 25%. Okay.